Okay, well, I hope you guys are all doing well. It's Friday. It's second week is all it's wrapping up. Last class of the week. Okay, so today I'm going to wrap up chapter 3. We're going to talk about box plots and so chapter 3 wraps up numeric summaries, descriptive statistics, and then I will begin chapter 4. Maybe you guys settle down in the back, please. So you have a quiz next week. So on Tuesday, you guys have a quiz in discussion. The quiz will cover up through chapter 3. So it covers, today I get up through box plots. Okay, I'll cover box plots. Box plots will, and the like, up through that will be on the quiz. When I start chapter 4 today, the chapter 4 stuff will not be on the quiz. All right, so let's talk box plots. Okay, box plots are another graphic display for numeric data. Okay, these box plots kind of show the bare essentials of the data. They show less detail than the other graphic displays that we have. What are the other graphic displays that we have for numeric data? Histograms and what else? And dot plots, okay? Shows less detail than histograms or dot plots. But sometimes that's what you want. Sometimes you want less detail. Okay. It just shows the box plots show kind of the bare essentials of the data. All right. So when we draw a box plot, you have a rectangle. This is the box. Inside the rectangle is a line. You have lines coming off of the box, and then maybe some circles. Okay. The box is defined by Q1, Q3, and the median. Q1, the median, and Q3 define the box, which means the width of the box is equal to what? The IQR. The distance between Q3 and Q1, that's the IQR. So the width of the box is the IQR. This line that comes out, this is called the whisker. The whisker extends to the largest point that is not an outlier. Okay, or here's also another whisker. This whisker goes to the smallest point that is not an outlier. Okay, and data out here, if you've got dots, these are outliers. This here would be an outlier also. The leftmost data point, in this case, this is also the minimum. And this is our maximum. Okay? And if you didn't have outliers, then the whisker would extend to the minimum or maximum. Okay? All right, so this is kind of the box plot. Of course, the box plot won't have all of these labels. It'll just be these black lines, just the rectangle with the whiskers, maybe some outliers. Yeah, question.
Can you determine when something is an outlier?
Yeah, that's actually my next slide. So, okay, is that good? All right, so yes, how do we decide what is an outlier, right? Okay. Okay, so with the box plot, we have these invisible boundaries. Invisible boundaries, which we will call fences. Okay, data inside the fences are not outliers. Data outside the fences are considered outliers. Okay, I guess technically we should say that they are potential outliers because what we call an outlier, not an outlier, maybe there's a little bit of subjectivity to it. Okay, so we're going to have an upper fence and a lower fence. The upper fence is equal to Q3 plus 1.5 times the IQR. The lower fence is going to be Q1 minus 1.5 times the IQR. All right? So let's say this is my box. Okay. So the median might be in the middle of the box. It's not necessarily in the middle of the box. Okay, the median can be anywhere, right? So on the previous one, the median is kind of off to the side. In this situation, the median happens to be in the middle of the box. Okay. And so the width of the box is the IQR. So what I'm going to do, so this distance, this is the IQR. And so what I can say is I'm going to take this IQR and I'm going to go 1.5 times the IQR above Q3. So we'll say right there. Do this. Okay. So this is 1.5 times the IQR. So if I start at Q3, and I go 1.5 times the IQR. This takes me out to here. So this location, this is my upper fence. We do the same thing, but in the opposite direction. And I will go 1.5 times the IQR, but below Q1. Okay, so here's Q1. I'm going to go 1.5 times the IQR this way. And this takes me down to here. This is my lower fence. So if it's beyond this, these would be considered outliers, and we would draw them with dots. Okay? If so any data outside of the fences, those are considered outliers. The whiskers go to the largest and smallest data points that are not outliers. So that's what we have. Alright, is that okay? So this is how we decide what the upper and lower fence are. So just a few other things. Okay, so box plots can tell us if our data is skewed. Okay, we would expect the tail there to be outliers in one direction and a long whisker. Okay, so if it's, for example, if it's right skewed, what we would see is something that looks like this. So right skewed, you have kind of a long whisker and outliers to the right. Okay, so that would be an indication of right skew. Left skew would just be the flip of that. And on the other hand, but box plots cannot tell us if it is unimodal or bimodal or multimodal. Okay, box plots do not tell us if the data is unimodal or bimodal. Okay? It can tell us if it is skewed or not. Alright, so keeping in mind what is Q1 and Q3 and the median and all of that, let's just try a little bit of, just a tiny bit of practice here. Alright, so let's create a box plot, and so here's going to be a number line. We'll start off at I don't know, 50, 60. Not that it matters, but we'll, 70. Okay, so let's say one box plot goes, let's say from here to here. Okay, and then another one draw some. Okay, so we'll say these are test scores. This will be we'll say test 1, and this will be test 2. Okay, so these are box plots of 2 different test scores, and we'll make a clicker question. All right, and so the question will be, I don't know, what percentage of students scored 80 or lower on test 1? Okay, so we'll say your options are, so turn on your clickers. Okay. All right, so go ahead and get your answers in. What percentage of students scored 80 or lower? If you want to talk to your neighbor to discuss, that's fine. Okay, so on test 1, what percentage of students scored 80 or lower? Okay, so we'll, if you're on the video, I'm going to just pause right here. All right, I'm going to go ahead and close the poll here. Okay, yeah, I would say that's correct. Okay, so scored 80 or lower, so this is right here. This is Q3 on test 1 at 80. 80 is at Q3, and so therefore we would say 75% of students scored lower than 80 or lower on test 1. Okay, I could ask other questions, and I can say, what if the question was, what percent scored lower than 80 or lower on test 2? You would say, this is not a clicker question. Just okay, and you would tell me, okay, at 80 on test 2, this is the median for test 2, so we would say 50% of students. Okay, because 80 is equal to the median. I could ask, what is the IQR for test 1? Okay, and so let's just eyeball this, and let's say this location right here, let's say this is 68. Okay, so if that's 68, what's the IQR? IQR is Q3 minus Q1. We would do 80 minus 68, and we get an IQR of 12. Yeah? Okay. And so where is the upper fence for Q1? I'm sorry, not for Q1, for test 1. Where's the upper fence for test 1? Okay, and your answer is? What's that?
95.
Not 95. 98, right? So it's going to be Q3 plus 1.5 times the IQR. So I go, Q3 is 80 plus 1.5 times the IQR, which we found to be 12. 1.5 times 12 is 18, plus 80, this takes me to 98. So I have a kind of an invisible fence right here. This, of course, doesn't actually show up in the box plot itself. Yes, question?
Going back to what percent scored 80 or lower on test 2, 50%, can you just explain that real quick?
Yeah, so on test 2, if we look at test 2, you know, the box has 3 lines. This is Q1, this is Q3, and this line right here is the median, right? And so my median is 80, right? So I'm asking what percentage of students scored at the median or lower. So the definition of the median is that half of students, or half of your data, is at the median or lower. So because for test 2 the median is 80, we can say 50%. Scored 80 or lower. Yes, question? Yeah, the upper and lower fences are not the whiskers. So it looks like my whisker ends at, I don't know, 95 here, okay? So that means the highest score on test 1, other than this guy, or this person, other than this person who scored 100, which is considered an outlier, the highest score on test 1 was, the next highest would be 95, okay? So the highest for test 1 is equal to 100, and that's an outlier. And then the next highest looks like it's 95, okay? And the whisker only goes to actual data points. It doesn't go to the fence, it goes to the actual data point, the largest data point that you had that wasn't an outlier. In that case, it's a 95. Okay, so my upper fence is at 98. If we did the same thing, my lower fence would be at 50. Okay. Yes, question?
So, anything between 95 and 98, what would that be?
Anything between 95 and 98 is what?
Like, what would that be considered? Would it be like on the
Yeah,
whisker?
it's, well, if there were a data point there, if somebody had scored a 98, okay, then the whisker goes up to 98. Okay? But we're saying there was no data here. There was nobody scored here. But if somebody had scored a 97, sure, the whisker goes to 97. If someone scores a 98, sure, the whisker goes to 98. And if someone scores a 99, then that 99 gets represented with a dot, because that would be considered an outlier, because it's outside of the fence. So the whisker can go up to the fence, but not past that. Okay? Or if I said, you know, what percentage of students scored between 68 and 80 on test 2? What percentage of students scored between 68 and 80 on test 2? You would tell me 25%, okay? Because I've got 25% between Q1 and the median. I also have 25% between the median and Q3. I'll have 25% above Q3, and I have 25% below Q1. Is that okay? Yes, question?
Is the 25% the standard for all box plots?
So the 25% comes from the fact that the box plot is defined by Q1, the median, and Q3. Okay, so all of the box plots have Q1, the median, and Q3, and so that breaks up your data into 25% chunks. Okay, the 25% includes any outliers too. Okay, so when I say 25% are above Q3, that also includes this person who scored 100. Yes, question?
Let's just say like no one got 90, but someone got 95. Does the whisker go till?
Yeah, the whisker just goes straight. So we don't, all we know is that somebody scored 95, and we have no idea if anybody scored a 90 or anything in between. We just know that 25% of the data is somewhere in this zone here, okay? So they all could be concentrated here, they all could be concentrated here, or they could all be spread out here. The box plot does not show that, okay? And that's okay. The box plot just tells you, here's Q1, here's Q3, here's the median. These ones are outliers. This gives you a sense of the data. Okay? If you want to know like how many scored in this zone, you're not going to get that from the box plot. But just we can look at these two box plots and make quick comparisons, and we can say, all right, which test was easier? Which test was easier here? Test 2, right? Because here, 50% of students scored over an 80, and with test 1, only 25% of students scored over an 80, right? So test 2 would be easier in that scenario, okay? The median for test 2 is 80, the median for test 1 is 75, so, you know, that's what we have there, okay? All right, so you've got to, yes?
So the last 25%, does that include the outliers as well?
Yes, yes, okay? 25% of the data, including outliers. Okay, we got to go on. If you have more questions about Boxplots, you can ask me during office hours. But I got to start talking about this other stuff. All right, so that we'll wrap up chapter 3 right there, and now we're going to start chapter 4. Okay, so chapter 4 is not covered on the quiz. That's okay. And chapter 4 is it's still under descriptive statistics, and it's all about describing a relationship between two numeric variables. So the idea here is we've gathered data, and for each observation, you know, we've gathered several variables, but at least 2 of them are numeric variables, okay? So, you know, we gathered data, and we have 2 numeric variables. And we want to know, is there some kind of relationship, okay? So let's just, for example, let's pretend we are studying snakes, okay? So we will look at several specimens of a certain species of snake. Okay, and for each snake, we will record the length and the weight. Okay, and so, you know, this is snake 1, snake 1. I'm drawing a picture. There's a snake, okay? And then snake 2. This is hard work, guys. All right, and here's snake 2, okay? And so, and they're, you know, I'm very proud of my snakes here. All right. So snake 1 we can see is longer, and if we had to predict the weight, which one would you think weighs more than the other? Snake 1, right? We expect, right? Is there a relationship between the length and weight? A relationship between length and weight, and we expect longer snakes to weigh more than shorter snakes. what's a good name for a snake? If we were to get. Okay, so we'll call length. We'll pretend we've gathered length and weight. So length we will call x, weight we will call y, and so I don't know how much do snakes weigh? I don't know. So all right, we'll pretend this is 12 inches, and then the weight, I don't know, 14 units of whatever. Okay, 14 inches and 16. I'm just making up some numbers here. 10, 10, 8, and 9. Okay, and so what we can do is we can make a scatter plot. And what we do is we say, okay, 12 and 14, we just plot them as coordinate pairs, and so I think, we got a snake right there. 14 and 16 gets a dot right here. 10 and 10, put a dot right there, and then 8 and 9 gets a dot right there. Okay. And so this is called a scatter plot. And sure enough, it looks like longer snakes weigh more than shorter snakes. That makes sense, especially if they're the same species of snake. Okay. Remembering, okay, never mind. All right, so when we talk about a relationship between two numeric variables, there are a few things that we want to talk about. Okay, so when describing a relationship, but this is between two numeric variables. Okay, so the first thing, there are three things we should talk about. Okay, so the first one, the shape of the relationship. And the shape of the relationship we're going to just say is either linear or nonlinear. And when we say linear, we mean a straight line. Shape of the relationship, then we'll talk about the direction or trend of the relationship. And this can either be positive, negative, or neither. And then we will have the strength of the relationship. Okay, and we can say this is either strong or weak or something in between. Maybe we would say that's moderate. Okay, so let me just give you some examples. For when we talk about the shape of a relationship, we're only going to concern ourselves with whether the relationship is linear or nonlinear. Okay, and a linear relationship means that a straight line can summarize the data. So, you plot your data. Okay, and you're okay. It looks like a straight line fits through the data. Okay, so how do we decide if something is linear? Okay, so you should always create a scatter plot. Scatter plot first, and then you just look at the scatter plot and decide if it looks like a straight line or not. Okay, then look at it and decide if it is linear. And this seems like a low-tech method of deciding whether something is linear or not, but it's like the best method. Okay, our eyes are really good at detecting patterns. Okay, you look out there and you can say, oh, they look like they line up in a straight line, or they don't. Okay, our eyes are very good at this, right? You drive past cornfields and you start seeing lines everywhere, right? So it's better, there are sophisticated tests and algorithms that we can run to say if it looks like a line or not, but our eyes do a better job most of the time, in fact. Okay, and then so that would be linear, and then anything that doesn't look like a straight line we say nonlinear. Okay, now if you were taking a more advanced class, you might subcategorize the nonlinear ones as exponential or geometric or I don't know, sinusoidal, whatever. It doesn't matter. We're just going to say, hey, if it doesn't look like a straight line, it's nonlinear. Okay, so if you get something that looks like this, all right, you can say this is nonlinear. Or you get something that goes something like that. Okay, there's some kind of trend here, but it's not a straight line. Okay, so these would just be nonlinear. Straight line does not work. All right, that's easy. Okay, so let's we'll try a clicker question here. All right. All right. So think about our population here, or our sample, will be taken from people in the United States. So this includes children, teens, adults, seniors, everybody. Okay, just people in the United States. And we are going to record two variables: the age in years or whatever, I don't know, and the other variable will be the person's height. Okay, and so here's your question: is this relationship linear or is it nonlinear? All right, I'll go ahead and start the question. You can discuss with your neighbor what you think. Is this relationship linear, nonlinear? Let's call it back together. I'm going to close the poll here. So we'll hit stop. Okay, yeah, it is nonlinear. So if we plot age versus height, okay, generally, if we look at kids, every year they get taller and taller and taller. Okay, and so look, it starts off linear. Okay, but then around 15 to 20, something around there, people kind of stop growing, And so height would stay kind of steady. Looking across the population, you know, we get something like this. And then perhaps in you know, our seniors, maybe you know, they lose a little bit of height as they're, you know, as they get older. Okay, and so overall, a straight line does not work. Okay, so we would say however, if we limit ourselves, if we limit our data to, you know, let's say children age 3 to 15, you know, probably our data would be kind of in this zone right here. And from 3 to 15, we probably would see a linear relationship, okay? That as age increases, then the height increases, okay? So could be linear for kind of that zone from 3 to 15. All right, so that's linear versus nonlinear. Now let's talk about the direction of the relationship. So a direction can be either positive or negative, okay? So positive means that in general, large values of x go with large values of y. And small values of x go with small values of y. And so a positive relationship would look something like this. Okay. Or if I mark on the x-axis, down here this is small x, and over here this is large x, and over here this is small y, and up here this is large y. Okay, we see down here small x goes with small y, and up here large x goes with large y. The negative direction is just kind of the reverse of that. And again, in general, large x goes with, I'll just draw an arrow, goes with small y, and small x goes with large y. Alright, so we have data kind of going like this, where when we look at, you know, small x, it goes with large y, and over here large x goes with small y. Okay, so that would be positive and negative directions. So an example of positive was snake length and snake weight. We expect long snakes to weigh more, short snakes to weigh less. Over here, we could think of used cars, and we can have odometer mileage, and sale price. Okay, if the car has very high odometer reading, we expect the sale price to be low. If the car has a low odometer reading, we expect the sale price to be higher. All right, one more slide with our last 1.5 minutes, 90 seconds, okay? Okay, and then so lastly we have kind of neither positive nor negative. Okay. So if you have something that's kind of like this, right? So maybe X could be shoe size, and Y could be hours of TV you watched yesterday. Okay, we would not expect to see a relationship between X and Y. All right, so that would be neither positive nor negative. We might, something like this would also be neither positive nor negative. Okay, this is also neither positive nor negative. However, if you have a situation that, I don't know, your data the data that you've recorded goes kind of like this, okay? Looking at the data over here, this would be kind of positive-ish, okay? Positive-ish relationship, okay? Because we don't want to assume that it's going to keep going down, or we don't know what happens out here. It hasn't been observed, so it seems, as far as we know, the large X seems to go with large Y, and so that's why we would say this is positive. But these would be neither positive nor negative. All right, we'll end there. Have a good weekend, you guys, and we'll see you on Monday.